All right, so today we're going to take a look at some other forces and some help with problem-solving strategies. So here we have a list of different forces that we will typically see, or names of forces. So if you see a problem that says a push, pull, thrust, lift, weight, friction, tension, all of these things, if you want to list them out, are types of forces. We haven't really dived too far into some of these. We've talked about thrust, we defined it on the last notes. Of course, push, pull, those are your standard names for forces. We've talked about lift a little bit. We've talked about weight a little bit too. And we've talked about, we've mentioned friction, we've mentioned tension, but we're going to do a little bit more with them. So first of all, weight, again, it's the force of gravity, if you want to write that down. But here we're really focusing on what the normal force is. And the normal force isn't just the force that counteracts the weight. Now, typically that's what we've seen, but that's because everything we've seen so far is on a flat surface, not on an inclined plane. If something is on an inclined plane, then our normal force is going to change. It's not just going to be the force that counteracts just the weight. It's going to be the force that's going to counteract a part of the weight, more than likely, but typically it is just going to be perpendicular to the surface of contact, and that's what we're going to see here. So the force supporting a load is perpendicular to the surface of contact between the load and its support. It is the normal force. Now they use the letter N, a capital N, to represent it, but it says this is not the unit for force N. Right. Oops, sorry, didn't mean to click on that. My finger wasn't even pointed at it, but let me re-highlight what you need to write. So this sentence here. So again, we don't use the symbol N for normal force because if you have something that says, oh, the normal force is equal to 20 newtons, well, that could be confusing. So we don't do that. Even though the text might do that. That can be a bit confusing. So I don't want to force confusion on anybody. Confusing. So instead, what we're going to do is we are going to use Fn for our normal force, as we've mentioned before. That way it can be equal to 20 newtons, and that's not confusing at all, because this one is our unit. Now, it does say on here that the normal force can be less than an object's weight if the object is on an incline, as I mentioned before, and we'll see that on our next example. So the supporting force acting perpendicular to and away from the surface is called the normal force. All right, so here we have our example with this incline. We have a skier skiing down this incline, and you can see there that our normal force is acting perpendicular to the surface of contact. So that changes things up a little bit. So our skier, including her equipment, has a mass of 60 kilograms. We want to know the acceleration if there is no friction, and then if there is friction that's 45 newtons, what is her acceleration? So let's go ahead and grab a screenshot here. I'm going to focus all my work down on the bottom there as much as I can. So here we have our free body diagram. You can see that the weight, now they use some symbology that I don't like. So I'm going to clean this up a little bit. Don't like to use W for weight either, because that also can be confusing later on when we start talking about things like work or power, whose unit is watts, or even when we talk about circular motion, get into angular velocity. That's an omega, which is kind of looks like a W. So on our coordinate system there, on to the left, I'm going to add that this is the positive y direction. This is going to be the negative x direction. I'm going to make that the negative. That way, going down the slope is the positive x direction, and going into the slope is the negative y direction. So we also have, of course, our normal force. The weight we use Fg for. This is our Fg in the x direction. And this is Fg in the y direction. So labeling those in the other picture, Fg, Fgx, Fg, not picture, but the free body diagram. There we go. So there we go. Now what we want to do is we need to deal with the force going down the slope, which is going to be the x direction. And so we have two different scenarios here. So I'm going to work on the left side of the screen here. First, when we don't have any friction. So the free body diagram is a little bit different here. We have our normal force. My angle might be off a little bit, but we have our weight in the y direction, weight in the x direction, and that's it. There's no frictional force here. So the weight in the y direction and the normal force are going to counteract each other. So again, normal force doesn't always counteract just the weight, but it does counteract parts of the weight sometimes. And so her weight going in the x direction is what's going to be pushing her down the slope, right? If you're weightless, then you're not going to slide down the slope. So that's where some trig is going to come in. So we need to deal with that. So there's our weight normally. We have this angle that conveniently is the same angle as the angle of the incline. It's kind of a nice thing that geometrically works out for us there. But trigonometrically speaking, we usually use cosine with x, sine with y. In this case, though, that changes. So that x portion is actually going to be the sine this time, because the x portion is the opposite to that 25-degree angle. So instead of saying that Fg is equal to cosine times, or Fgx is cosine of the angle times the weight, it's going to be the sine. So Fgx is what we're looking for. Sorry about that. So there's what we're looking for. Now remember, Fg, as always, is mg. G is our gravitational constant, 9.81 on Earth. And m in this case is the mass of the skier, which is 60 kilograms. So plugging everything in. Now this is just the forces. We want to find the acceleration. Sorry, I forgot about that part of it. So this is our net force as well, because it's the only force acting that's not counteracted by something. Our net force is also equal to mass times acceleration, which we are looking for the acceleration piece. So our ma is equal to mg times sine of 25. But now notice something. We have m on both sides. They're going to cancel each other out. So really, her mass doesn't matter at all. So our acceleration is really just gravity times sine of 25, or 9.81 times sine of 25. And at this point, we're ready to go to the calculator with it. I can't pull up a calculator on the screenshot screen here, so I have to just trust my calculations here, I guess. Again, whenever you're dealing with sine, cosine, tangent, you want to make sure you do have your calculator in the right mode. And that is degree mode when we're in degrees. So 9.81 times sine of 25 comes out to be 4.14 meters per second squared. Now, that's in case we have no friction involved. If we do have friction involved, our free body diagram changes a little bit. So I'm going to switch over and I'll put the whole thing up at the end here. So now we do have a frictional force counteracting it, which means really there's only one change. The net force is still the same as it was before. It's still mass times acceleration, which is the 60 times our acceleration that we're looking for. But it's also going to be equal to the FGX, which is what's going down the slope, minus our frictional force. And our frictional force, we know, is 45. Everything else is the same. FGX is still mg sine of 25. M and A, they're still there, so we can plug everything in. MA is equal to mg sine of 25 minus our frictional force. We can plug everything in. And in this case, the 60s aren't going to cancel each other out, so kind of got to leave it there. Got to divide by 60 on both sides. Let me mark it. Oh boy, here comes an announcement.
Students, you have 1 minute to get to class.
So we got to divide by 60 on both sides here. And at this point, it's pretty much easier to just go ahead. Oh, that kind of okay. It went back. Go ahead and plug everything in the calculator. So 60 times 9.81 times sine of 25. All that minus 45. All of that divided by 60. Comes out to be 3.396 meters per second squared, which does make sense. We got a lower acceleration than we had before, which is good because we got a lower acceleration there, which is good because, well, we have friction counteracting that movement, which so it's going to slow down our skier down the slope. And here's our two calculations together. Didn't mark this as part B, but there we go. And there you have it. So this one here kind of breaks down the weight into its components. I'm going to go ahead and screenshot this because I want you to write this on your notes, but I'm going to make some changes to it because, again, it has the a different version of what I like to have labeled here. All right. So again, we have this is the weight broken down, right? So this is G, This is FGY, FGX. So this you want to go ahead and sketch on your notes. So this is what happens to the weight of an object when objects rest on an inclined plane that makes an angle theta with the horizontal surface. It doesn't change, the weight's going to be the same. It's just now the only part of the weight that's counteracting the normal force is the y direction portion of that. That's it. Weight's weight. It's always going to be that. So this one here, we're looking at tension. And so tension is a special type of force that is specifically always a pull force. Now you can't push a tension, which is actually, it says here, you can't push a rope. So it's a force along a length of a medium, especially a force carried by a flexible medium such as a rope or cable. So the name similarly comes from the same Latin word meaning to stretch that tendons come from, right? You stretch and compress tendons in order to move joints in your body. We'll talk more about that here in a minute too. So here's an illustration of tension. You can see the person holding this mass. The tension forces counteract each other and the weight is down below. So if you look at the free body diagram of the mass, the tension and the weight counteract each other, which means the tension force is just the same as the weight, unless that person is moving it and moving it around more than the weight would not counteract that force. But there it is. As long as it's just being held into the air, then this is true. The tension force is equal to the weight. So another way to think about this, so this is talking about the finger joint, so using tendons and joints to bend and stretch out joints. That's what tendons do. But also bike cables. So here we have two pictures here. You can see the tendons in the finger there that stretch and compress depending on whether you're straightening or bending your finger. And then there's as well the tension in a cable on a bike brake. When you pull the brake, it pulls that cable, tightening the tension, and the tighter the tension goes, the harder the brake compresses onto the wheel, which doesn't show that part for some reason, but you get the idea. All right, so here we have the tension in a tightrope. So this problem takes a bit because there's some special things going on here that change it up a little bit than what we are used to seeing. So what we need to do here, I need to screenshot it for one. So we have this tightrope walker supporting that is 70 kilograms in mass. The wires sagging 5 degrees on both sides. They're in the middle, so that's how you know that if the angles are the same, then the tightrope walker is in the middle. And the tightrope walker is just standing there, not moving, so there's no acceleration. So what we need to do is look at the free body diagram, but maybe in a bit more detail than they show down there below. So they have this tension forces going out in the angles, but it's not really showing us the whole picture here. So it's got these tension forces. And then we have the weight. But these tension forces also have components because they are out at angles. So these are T1, TL, sorry, and TR. And those are in the x direction, TLX, TRX. And then going up, we have TLY and TRY. So those two are going to combine together to counteract the weight. So we again, this tightrope walker is not moving, so our net force is 0, which means that TLY plus TRY minus the weight is equal to 0. So we move that weight over, the weight is equal to TLY plus TRY. Again, we know FG, as always, is equal to mg, which we do have the mass. We're not going to do anything with that just yet, but we will place that in there in a minute. I'm going to scooch over a little bit so I have a little bit more space, but we also know that the x directions are going to counteract each other because, again, net force in the x direction is also equal to 0. And that means that TL or TRX minus TLX is equal to 0, which means that TRX equals TLX. So now we need to get these into their components, and well, more so than they already are. They're already in their components, but we need to deal with them in terms of them being angles and using sine, cosine, and all that good stuff. So TRX, TLX, now we're back to being able to use sine and cosine as we usually do. The x parts are the cosine portions. So these two here mean that it's TR times cosine of 5 equal to TL times cosine of 5. So we could go ahead and solve one of these for TR or TL. It doesn't matter which one. And actually, doing so, we're going to divide by cosine of 5 on both sides. That's just going to cancel it out. TR is equal to TL. All right, so that means that we can look at the y direction again, and shift this over to the other side here. So looking in the y direction, TLY is going to be equal to TL times sine of 5. And TRY is TR times sine of 5. But we know that TL and TR are the same, so really these two things are going to be the same as well, right? TRY and TLY are going to be equal to each other as well. So in our original here, FG is equal to 2 times, it doesn't matter which one we plug in, TLY is just fine. So sorry. FG is equal to 2 times TL sine of 5. Again, we know FG is mg. And we know m is 70 times 9.81 equal to 2 times sine of 5 times TL. So we're doing a little rearranging. I'm going to divide both sides by 2 sine of 5. So now I have, sorry, I'm running low on space on this side here. There we go, though. So now we're down to this 70 times 9.81. And dividing that by 2 times sine of 5. So TL, which means TR as well, is equal to 3,939.5 newtons. So that means that is also what TR is as well, if you want to write that in there without that box. So here we have the formula that we pretty much just used, where W is the weight of the tightrope walker divided by 2 times sine of theta, and that can work as long as the weight is the force that's actually perpendicular to the tightrope when the tightrope is not being bent. But there also, you could just use whatever force is causing that to happen. So these two formulas here, really the bottom one is the main one, because that force perpendicular could be the weight, and that's fine. But this is a specialized formula for just this problem type when it is specifically in the middle of the connector, the flexible connector. It does not work whenever that is not the case, and we'll see a problem like that later on. So here's another example. So you can see there again, the force is at the middle of the chain that's connecting the car to the tree. To pull that car out of the mud, I guess is what it's stuck in over there. I'm not real sure. Sand? It says mud. Okay. But there you go. That same situation can be applied, just have to use a different force instead of the weight. Now, these flexible connectors are all over the place, so we can see them here with the Golden Gate Bridge. Or any suspension bridge really, that they have very heavy flexible connectors, which cause them to sag. So they don't have a straight line going from them, but they do they have that bit of a curve to them. And that is their characteristic shape. So this next part is about inertial frame of reference and these things called fictitious forces. Examples would be like cars slowing down, going around in a merry-go-round. They arise simply because an observer is accelerating in a frame of reference such that one rotates or undergoes linear acceleration. For example, a satellite is heading, here we go. The real good example here is the satellite one they have listed here. So a satellite is heading north, and you look at it in a telescope, but to you it appears that it's also going off to the right. And the reason it's doing that is because it is also, the Earth is moving as well. So even though it looks like it's got this force making that satellite move north and to the right or west, it's not actually doing that. It appears that way because Earth is also moving, making it appear to be moving a different direction than it really is. Now, The crucial factor here in determining whether a frame of reference is inertial or whether it accelerates or rotates relative to a known inertial frame. Just keep in mind that all the forces that we are looking at are real forces, but there are other real forces that we don't bring up, like lift or thrust, and they are a little more specialized, that they need a little bit more calculus to really deal with them in a proper way. So moving on here, we have these problem-solving strategies, and we're going to kind of just go through these fairly quickly, just to finish out these notes. First thing is step one, when you're solving problems with Newton's laws of motion. So step one, draw a careful sketch of the situation. Use arrows to represent all forces and label them carefully. Make their lengths and directions correspond to the forces they represent, right? Making sure that your sketch is accurate and showing those forces that are acting on whatever you're looking at. So here we have this example here. That way you can make sure you're isolating what is important in the problem as long as your drawing is accurate. So of course the arrows here represent forces. Step two is to identify what needs to be determined and what is known or can be inferred from the problem as stated. So write down the list of the knowns and unknowns. It's really what this one's trying to say. Step three. Now it says once a free body diagram is drawn, which you can do with step two as well, or step one when you're drawing the other sketch. Now you're going to apply Newton's second law, F equals ma, to the situation. And there's Newton's second law again. Sometimes it's zero, sometimes it's a specific direction to that as well, depending on the problem. So if we were looking at the one we just saw, we'd really only be working in the y direction. And step four, check to see if the solution is reasonable.